Good afternoon. This is Professor David J. De Los Reyes, an electrical engineer by profession, had been a professor for electrical engineering and had been an electrical engineering head for quite some time, and an electronic troubleshooter also. So I do analog and digital TVs. I could troubleshoot that switch mode power supplies, a direct current power supply, amplifiers, electric guitars, to name a few. Okay, let's proceed. My lesson for this afternoon will be lesson number 98. We are almost on the photo finish on the integral calculus subject. Integral calculus, the subtopic is surface of revolution. And the topic for this afternoon will be right circular cone. We will derive the formula on how to compute for the total surface area of the slant height of a right circular cone. Even the total surface area, because the total surface area for a right circular cone will be the total surface area of the slant height plus the area of the bottom. So if you are designing a container in the form of a right circular cone, you will know how much material will be needed in the so-called surface area. Okay, let's proceed. I will try to read the problem, guys. Derive by integration the surface area of the slant height of a right circular cone. Excuse me. Let's try to bring out the figure of a right circular cone on the Cartesian coordinate system. So this should be the y-axis, this is the x-axis, this is the right circular cone, these are the slant heights, and this is the base. Since a right circular cone is actually a solid thing, okay, I will try to draw the arch at the bottom. So this is actually the bottom portion. It got a little arch. It is solid, okay? It will contain volume, okay? The dotted line will be the arch at the bottom portion. The problem is asking for the total surface area of the slant height, meaning the surface area going around, okay? And if the problem is asking also for the bottom area, there's no problem because the bottom area is just actually a circle. So actually, our answer here contains two equations. The first one is the total surface area involving the slant height. And the second formula, it got a subscript T, meaning the total surface area. It should be the surface area of the slant height plus the area of the bottom portion. Okay? The area of the bottom portion, we do not need integration anymore. It will just be simply pi r squared. It is a circle, right? So the total surface area is actually the area of the bottom plus the area of the slant height. But for the meantime, we will derive the formula for taking the surface area of the slant height. Okay, let's proceed. This point here should be with coordinates r and 0. This is r. The ordinate will be 0. This point here on the vertex of the cone, the abscissa is 0 and the ordinate is r. So the coordinates will be with the designation 0 and r. Okay? This is negative r and 0. This negative r, the significance is that it is on the left side. But we do not need this one. Okay? We will draw a horizontal slice. Okay? Then we'll try to rotate this one complete revolution with respect to the y-axis. So actually, we are rotating the surface area one complete revolution with respect to the y-axis. Okay, to take the total surface area. Then we will move this differential area from this point here to this to cover up the total surface of this slant height. Okay, let's proceed. We'll compute first the length of arc for the what they call this slant height. Okay, because this part of the graph, this portion here is actually ds. The length of arc for the slant height of the slant height of the right circular cone. And we are just lucky, the slant height is actually a straight slant vertical slant line, okay? Okay, let's try to bring out the formula, one of the formulas for taking the slant height. We will take case number 2. Differential length of arc is actually the square root of 1 dx dy quantity square times dy. This is dy, this should be dy. I will use this one. I will not use the dy dx. I will use the x over dy. Where differential s is actually the length of arc of the cone. Okay? If we will try to project the right triangle here, we will project the bigger right triangle, it is this one. And the upper portion, we will project it. The upper portion will be this one. Horizontal line, same angle, same line. So if this is theta, this should also be theta. This height here is h, this is r, this is y, and this is x. So actually we are given two right triangles, and they are they call it congruent or whatever the name will be. For me, I don't be bothered with the congruent thing. I will just say if this is theta, this will be theta, because this is horizontal, and this is the same straight line. So if this is theta, this should also be theta. Sorry for that one. So taking the tangent of the theta, using the bigger right triangle, it will be opposite over adjacent, h over r. And using the smaller right triangle, it should be this side here, h minus y over x. Then we'll try to compute for x. Algebraic manipulation, right? X will be r over h times the quantity h minus y. On the formula for the differential length of arc, we need the x dy quantity square, okay? We are now given x. So taking the differential with respect to y, okay? Dx over dy will be equal to, radius is constant, altitude is constant, so it will be r over h times the differential of h minus y. The differential of h with respect to y is 0. The differential of y with respect to itself is negative 1. So dx over dy is actually negative r over h. Okay, we need dx over dy quantity square, so we will square both sides. Dx over dy quantity square is dx over dy quantity square equal to negative r over h quantity square. Negative, that will be positive r square. H quantity square will be h square. Equation number 2. This one we call it equation number 1. I just mark it as equation number 1 because later on I will try to go back there. Okay. Therefore, if we will try to take this value of equation number 2, we place it on equation number 1, differential length of arc now will be equal to the square root, okay, of 1. I am following this. Dx over dy quantity square is r square over h square times dy. Simplifying the terms inside, 1 times h square is h square plus r square all over. The bottom portion is h square. It's a perfect square, so I take the square root of already, so that will be h. So differential length of arc for right circular cone is actually the square root of r square plus h square, okay, over h times dy. I will call this as equation number 3. Why I mark it as equation number 3? Later on, I will go back to this, so it could be easy for my eyes to go back, okay? I will take case number 1 for the so-called surface of revolution. Differential surface area rotated with respect to the y-axis. That's why it has got a subscript y equal to 2 pi times radius times thickness. You go back here. To compute for this total area, you take the circumference here times differential length of arc. Okay? I just multiply this 2 to take the total surface area. If you try to unwind it. Okay? So this will be 2 pi. The radius is actually, the radius of the variable area is actually x. This is x. This is x. Right? So this is actually 2 pi. The radius will be x times ds, differential length of arc. We now know differential length of arc. It is equation number 3. It is the square root of r square plus h square over h, okay, times dy. And if you try to inspect it, the variables on the right hand side contains y and x. So to take the integral, we must have to replace x in terms of y. But we know the relation, we'll go back here. Okay? So x is equal to r over h times the quantity h minus y. Therefore, differential surface area rotated with respect to the y-axis equal to, I just compress the constant terms. 2 pi, the square root over h. 2 pi, this is square root over h, times the value of x. But what is x? It is r over h times the quantity h minus y plus quantity times dy. R over h is again a constant, so I will try to compress again the constant terms. So this should be 2 pi r. The bottom portion is h and h, this is h squared, multiplied by the quantity r squared plus h squared times the quantity h minus y dy. Our upper limit will be h and the lower limit will be 0. Okay? Try to see the figure, guys. To compute for the total surface area, y should move from 0 to h. So our lower limit is actually 0 and the upper limit is actually h. Okay? So I place it here, upper limit is h, lower limit is 0. So if we try to take the integral of both sides, okay, this should be with the limit from 0 to h. The integral of the differential s of y is just s of y, the total surface area of this slant height, equal to, I just write this one, sorry for this one. This should be after the pure constant. I will place it here. Okay, this is from 0 to h. Because all these terms are constant, okay? Okay, so I will write the constants, which comprises of r and h squared, times the integral from 0 to h of this one, h minus y times dy. Pure constant. The right hand side, it's an easy money. H is constant, so the integral of h dy will be hy. So that's hy, right? And the integral of y dy will be power formula. That will be y squared over 2. Okay? We pass by the different integrations. This is an easy term, okay? So this is y squared over 2 with the limit from 0 to h. I will rewrite the constants times, I will try to put the upper limit, this will be h squared minus h squared over 2, that's the upper limit. And if you try to place the lower limit, the operation here is multiplication. And if we place y to be 0, this will be 0 and 0. So actually the lower limit is minus 0. Or the lower limit has nothing to do with the final answer. Okay? So I will rewrite the constant terms times 2h squared minus h squared is h squared. This is all over 2. And luckily, this h squared cancel with this. And these two here cancel with this. So the final formula for taking, this is with the subscript y. The total surface area of the slant height for a right circular cone, this should be pi r times the quantity r squared plus h squared, square units. Square units, guys, not units. A unit length times a unit length will be square unit length. So this should be square units. So the slant height formula is this one. And if you try to Google it, okay, if you try to Google it, on Google, it bring out a formula for the total surface area. It is the area of the base plus the slant height. The area of the base, it is a circular thing. We are given the radius, so this should be pi r squared. And the total surface area of the slant height, as per our computation, it is pi r, okay, times the quantity r squared plus h squared. So this is actually the total formula for taking the total surface area of a right circular cone, including the base and the slant height. So I will repeat it for the last time before we go this afternoon. The total surface area of a right circular cone will be the area of the base plus the surface area of this line height. As per our computation, this is pi r times the square root of r square plus h square. Okay? Is it correct? Pi r square plus pi r times the quantity. This is the area of the base. This is the area of the slant height. That's the total surface area. Because if you are the project engineer and your boss is asking for the total surface area of a metal thing needed in the construction of the right circular cone, which is a container maybe, okay, you use this formula. Okay, good afternoon, Los Angeles. That's the formula for taking the total surface area of a right circular cone, area of the base, plus area of the slant height. Pi r square plus pi r times the square root of r square plus h square. Okay, good afternoon, Los Angeles.